What chapter are you
We're in chapter 13. Well, welcome back, everyone. We're now on, I believe this is week 10 out of 16 weeks. So this is the part of the semester where it seems to fly by really, really fast. Well, any questions at all, folks, to get us started out today? Okay, just a couple quick announcements. We have our quiz 8 posted. Quiz number 9 is going to be based off something in chapter 13. I haven't decided on what the best quiz will be yet. And another, just an update with the class. I think this only affects 2 people, but just in case I'm wrong, this is a good statement for the whole class. If you opted out of the book bundle, you saved money in this class, but this is not working as intended. What's supposed to happen is to purchase access, you're supposed to be able to click on this, and then something eventually loads sometime. There it goes. And this is supposed to take you to the right thing to buy in the bookstore. It looks like for our class is sending us to just an empty spot. And I chatted with technical support on Friday, around Friday morning, but that wasn't too productive. All they provided me was a link. And when I shared that link with students in the class, it doesn't work. It acts just like this and eventually tells you go through Moodle, which again is not super helpful. So what I'm going to do on Tuesday morning, this is going to be probably my #1 thing to do, is just call technical support, try to get an actual human on, and see just what we've got to do to make this work. And it's getting to the point where this has to get fixed fast because we don't want to go more than another additional week without access. That would be really bad for learning point of view. But again, sorry for the struggles with this and all the trouble getting going. Any questions or information to add to that?
Sure. If you scroll down past where it says to click on, I gotta find your.
Mhm.
Let me see if I can do it that way.
Cool.
Let me put in the course ID.
There is a course ID for this class, which would be,
Yeah, but it won't, it's terminal based link.
ah,
Unless
yeah.
register for this course through your local campus version. So
Strange.
it's still not letting.
Well, that's the course ID right there at the top of Moodle, but
Yeah,
if something's broken
but that's
in
just what
the
it's
platform, then
you still have to go through Moodle to do it.
yeah,
So.
geez. Super frustrating. Sorry about that, folks. So we'll get this going one way or another. But aside from technology failing in spectacular ways, other questions at the moment? Okay, so however this works out, we should get access restored back pretty fast, I'm hoping. And if all else fails, we'll find just some alternative way to go. So no one should be losing points in this class because of screw up like this on technology. So that's my promise. We'll make it right one way or another. But with where we're at in chapter 13, here we're again connecting probability with what we're about to do with inferential statistics. 13.1 starts off kind of rough. So it's not as bad as it seems, but what makes it rough is it's a lot of conceptual questions. In fact, some of the questions are so little tricky that I actually wrote out a cheat sheet for one of them just to make sure, if I forget, we write down correctly to help with the homework. So let's give this section a try. It starts off like this. We've been dealing with quantitative data for quite a while now through the various chapters, but now we're returning to categorical data. So when it says sampling distribution model for a proportion, the word proportion right there already tells us we're dealing with categorical data. And the definition here makes it more firm. We start by saying an individual or object that possesses the characteristic of interest is called a success. One that does not possess the character is called a failure. This all just seems really kind of random, but let's add more context to this. We need notions of successes and failures because in chapter 13, the data is categorical, with outcomes. Success or failure. So essentially, that's what we're doing in this section. Exactly two outcomes for our categorical variable. Success is going to be the thing you're interested about in the study, and a failure just means that was the thing that we were not interested in. You know, that's the definition, but without an immediate example, it's still kind of foggy. So let's grab something that we've done in the past just to put it in context. So all the way back to chapter 1 again. Let's take a look at these data when we think about successes and failures. Right here on this example, pretty simple write-up. It says, San Fernando Valley residents are okay with the 1-cent transit tax. And this headline was based on responses for a sample of 100 San Fernando Valley residents. So what's going on here is they were polling the residents of San Fernando Valley, asking them if they're okay with the tax. People who respond, yes, they're okay with it, would be the success. That's the thing we're interested in, the proportion of people who are okay with the transit tax. And the people who respond to the survey saying, no, we're not in favor of the transit tax. Those would be the failures in the study. Does that make sense at the moment with the dichotomy successes versus failures? Okay, it's a really tricky language because most of the time we have context, but for describing a categorical variable in complete generality with no context, just so we can write down a formula, it's got to be in this way. So word of warning, a success is not always a good thing. It's a thing the study is interested in. So if the study is interested in, say, some rare kind of genetic cancer, that's the success. It just feels kind of wrong to call it a success when it's bad. It just means we're interested in that particular outcome. So we're in the land of successes versus failures. Our statistic is easier to calculate than the sample mean when we're dealing with quantitative data. We just take the number of successes that were in the sample, divide by the sample size, and we get the statistic p hat. So it's this way when you write it, p with a little, we call that a hat, so just an up arrow right on top of it. It's read as p hat. So that's our statistic. It measures the successes in the sample. And the thing that's trying to estimate is the parameter, the population proportion p itself, just denoted simply by p. So it's a parameter in the sense that it'll describe the population. But the issues with p is that p is typically unknown. It's a quantity that we want to try to estimate by pulling a sample, and we need to try to be very careful with that estimate by saying how reliable it is at the same time. That's what's leading us into confidence intervals. So we have p hat, this quantity here. We have p, the population proportion. Even though p is typically unknown, we can make the statement that the unknown, the true population proportion of successes p, whatever a success might be, it's approximately equal to p hat, the proportion of successes in the sample itself. And when we say proportion, it's kind of like what we meant when we say a probability of something. A proportion can be converted into a percentage or just left in decimal form, much like with probabilities. When we were back here on this simple example, we imagined, we were just making up data, but we imagined, suppose 63 are in favor of the transit tax, then p hat would have been 63 divided by 100. That's kind of just fine as a proportion. If we want a decimal number, we call it 0.63, much like a probability. As a percentage, 63%. And all of those are equivalent ways of saying the same exact thing. Well, any questions, folks, with this big wall of text here to start off this section? Okay, so here's an example that tries to put this into reasonable context. It starts off by saying, the article, Facebook Etiquette at Work from USA Today. This was in 2010 when social media was still kind of new in a certain sense. This article reported that 56% of people participating in the survey of social network users said it was not okay for someone to friend his or her boss. Just full disclosure, I think I tend to agree with that. I don't think I would ever friend my boss, but that's what people were saying way back in 2010, where I think there's more diverse opinions on that. Here it says, let P denote the true proportion of all social network users who feel this way, and suppose it's true that P is really 0.56. That's quite a statement, because we said P is typically unknown. Well, where did 0.56 come from? It came from the study where they said it's approximately 56%, but that was just P hat. So P is really still unknown. We don't have any way to describe how reasonable that estimate is, what the error is in making that estimate. So this is just a big guess. We're going to assume that this is the truth of the population, even though it's truly an unknown. That's the best information we have. So let's highlight that and just work from that point on. But by the way, when you read through all of this, one thing that's really critical about these problems is calculating p hat. And when you do that, you have to say that what the number of successes is in the sample. But in the very first place, we need to know what is a success in the first place. Any volunteers for saying what the success would be in this example? We can say a success is the outcome that a participant in the study says, well, this is about friending your boss, right? So I'll put a blank here for the moment. To friend their boss. So any volunteers for what should go there to complete this statement? Exactly. Here, if they said 56% of the people said, oh, I take that back. It should be the other way around, not okay, because of that right there. So it should be a success is the outcome of saying it's not okay to friend their boss. But you're on the right track. That was pretty much what it was about. And the reason I went this way, that it's not okay, is because that's how the parameter p equals 0.56 was given in this problem. If they say 56% of the people in a survey of social network users said it's not okay to friend his or her boss, and that's a way of saying this is the major interest of the study, the proportion that would agree with that, saying it's not okay. And that means that's what a success would be in this situation. We can say rapidly after that, a failure is when they say it is okay. Well, any questions, folks, on determining the successes versus the failures?
We assume that the failure is 0.44, or do we just leave it be?
It would be, yeah, absolutely. Usually the study or the statistical methods rather are always going to focus on the proportion of the successes, but there's formulas that come into play that go like this. We have a formula that goes this way. Standard deviation of p hat is p times q divided by n. P is the proportion of successes, but we use the complement rule and call q the proportion of failures. So in formulas, we do use them, absolutely. So notice that is the complement rule since it's 1 minus the proportion p, probability of a success. Other questions at the moment? Okay, so now we know what a success and a failure ought to represent in this situation. And here's where it gets a little bit foggy. These notes are pretty abstract in a real sense. Nonetheless, it's stuff that we have to describe to get through it. And what makes it really hard to describe is that estimate right there. We say the unknown parameter p is approximately equal to the statistic. we had a lot to say about that. We said, we have to describe how reliable that estimate really is in the first place. And then when we were in chapter 12, we said the hint at that is we use probabilities. So this is where probability is kind of just injecting itself right back into our statistical work. It's not easy to describe, but the normal model comes back into the picture. And this is what's going on in part B. Part B is not so much a real question I could ask as a quiz problem or exam problem. Think of this as a kind of demonstration or experiment that's trying to show us why this is true, the central limit theorem. This is the only statement in the statistics class I put in a box and a highlight like this, just to kind of emphasize its importance. And the major thing that's a surprise is that statement there. The sampling distribution of p hat is approximately normal. So the normal distribution enters the picture again, and that's how probability comes into this work. So to inch our way towards that, we have to talk about a sampling distribution. So I think that's where it gets pretty tricky. So the way this comes into play is they ask in part B, would p hat, based on a random sample of 50 social network users, have a sample distribution that's approximately normal? Well, that kind of depends on the sample size, but here's how we're going to do it. There's sampling variability that we have to worry about in the first place. And every time we go to calculate a statistic, like say this p hat right here, we get sampling variability. The reason is, you go to grab a random sample of 50 social network users and calculate the statistic once. Say sample one, let's maybe put that over here where it's a little bit more official. Say you take sample one, sample size is 50, and you calculate p hat. We don't know what that's going to come out as unless we calculate it, but let's just imagine, just for the sake of argument, that it comes out as 0.5. Let's take a look at that. Probably not going to come out exactly 0.56, but it could be something like 0.57, for example. That's if this is a pretty good estimate right here, if it's close to being true. When we go to get our random sample, if it's truly a random sample, we expect values close to the true parameter's value. But that's in one sample. We go to sample two. Critical thing is same sample size each time we do this to compare what could happen from sample to sample. And we could get something like p hat equals maybe 0.52. It could be way off the value of the parameter just by random sampling error. And the values of the statistics change from sample to sample. The reason that happens is these are random samples. The same 50 people don't make it to every single sample. If that ever happened, that would be like winning the lottery. And so we have different responses. They're all going to be close to this value if it's true, but this is what we mean by sampling variability. The value of p hat changes from sample to sample to sample. And what we want to imagine is doing this a lot. I mean, really tons and tons of times. So the way we're going to emphasize that is go dot to dot to dot, and maybe we're at sample 1,000, for example, or 10,000 or 100,000. No one has the money to actually do this. So that's why we're going to investigate it through an actual simulation to address this question. So that's what this is saying right here. But imagine someone did do 1,000 different samples, all of them with the same sample size, 50. They go to calculate p hat for the 1,000th time. It might be something like 0.54. So all these values should be close to this value. P hat is 0.56. Sorry, let me zoom out. Provided that really is a close value for the unknown population proportion of successes. This problem, it was people who said it's not okay to friend their boss on social media. So these values all change from sample to sample. And if we have something that's changing from sample to sample, but they're all numerical values, we can put them into a histogram. So let's say a histogram of these values approximates is just an approximation, but it's a great approximation if you have a lot of samples to deal with. It approximates the sampling distribution of p hat. So what's the sampling distribution? Let's read the official definition. It is abstract. So clear your mind, take a deep breath, and let's go through it. The distribution formed by the values of a sample statistic for every possible different sample of a given size is called the sampling distribution. So we imagine every possible sample of size 50 needs to be taken. Then every single p hat needs to be calculated from all the possible samples. Once you do that, you have the sampling distribution. It collects into one distribution all the potential values p hat could ever be. But that's just in words. We're going to do a real simulation so that we can actually see it happen, because seeing is believing. But any questions at the moment with sampling distribution? Okay, so at the moment, it's as if there are two populations. There's a population you're interested in, social network users, and finding the outcome of whether they think it's okay or not to friend their boss. But once you do this study, there's population 2. The second population is all the potential values p hat could ever be for your given sample size, 50 in this problem. And the collection of all these is the sampling distribution. So we're going to put it to use by doing a simulation. This is the second time we've done something along these lines. We've been using stuff like Excel before. So we're going to use something different than Excel, but same idea. You don't ever have to use Excel in this class for any credit whatsoever. These are always just purely for demonstration purposes. I feel like this is such a hard definition to crack that we need the simulation just to visualize it. So the calculator we're using this time is this thing. This is called RStudio, and the more statistics you take, the more likely it is you're going to use something like this. We teach a class 3350 called Statistical Methods, usually a second class after this one, where it's all about just using this instead of the TI-84. So here's what's going to happen in the simulation. Sampling distribution is going to go right here. That's where we're collecting all these kinds of values. So it's just going to be a histogram. But before we get started, here's what we put in to start it out. We put P is 0.56. That came from right over here. So that's the supposed value of the population proportion P. Next thing we're going to do is indicate our sample size. We're going to do this at sample size, say 50. Actually, let's start off at 5 and work our way up to 50. We know larger samples are important in statistics, but we'll get to see why if we start at a really, really low value. And here's where the weird part of the simulation happens. Again, this is all for demonstration purposes. You don't ever have to use this calculator again. I felt like I should say what's going on before we use it, just for the sake of helping out. So what this does is it collects here the successes in a sample size of size 5 into one spot. Then it calculates p hat. It takes the number of successes and divides it by n. That's just doing this right here. P hat, number of successes, divide by n. The mysterious part is this right here. It's using a random number generator from something called the binomial distribution to actually approximate this whole process of gathering successes when you have a supposed value for the true proportion of successes. So after all that's done, we'll have 10 to the power of 6 different values of p hat. So what is that? 1 million different values. Whereas over here, we were just describing 1,000 of them. We'll go for 1 million on this because why not make a computer work hard for us? And then we'll plug them all into a histogram. So that's what that line is saying. So let's write this out, or let's run this whole thing. And that's the result. Would you say that's normally distributed based off that picture? It almost looks like it, right? You could definitely put a curve to it. Curve would go about like this. But there's still an actual big problem. With a sample size of just 5, These are the possible values of p hat. And it turns out only certain values are actually possible. There's a huge gap right here where no values were ever obtained, even though we took a million different samples all at once. So it ought to improve from then on out. So let's double this to a sample size of, well, I guess that's tripling it, 15, and see what the change is. A sample size of 15, would you say that's an improvement or regression? Is this more normal or less normal? I would agree with you. The shape is about the same, but there's less gaps, right? That's what we're trying to see. We want something that looks like a real histogram with no gaps that is unimodal and symmetric. Sample size 15 doesn't quite do it. So what if we double that to sample size 30? At sample size 30, it got a little bit weird, but at least the gaps are gone. So that's starting to look a little bit more cleaned up. The curve that was drawn above here starts to look a little bit off, so let's just take that off. Now if we go to sample size, say 50, this is what they were really using in the problem, a random sample of 50 social network users. We bump this up to 50. Here's the picture we get this time. And you know, that doesn't look too bad as far as normal curves go. We placed normal curves on data that looked a lot less pretty than that and still said it's probably an okay approximation. This looks like an excellent approximation right at sample size 50. And just for the fun of it, let's say we went up to a sample size of 100. Sample size of 100, that looks almost perfectly like the normal distribution at that point. It seems to have the right curvature going this way and everything that you would expect. But that's cheating. We only were going to do sample size of 50. So that's what that picture looks like in that situation. So this is what we mean by sampling distribution. Let's put it down right here on the notes. The question says, would a p-hat based on a random sample of 50 social network users have a sampling distribution that's approximately normal? And we will say to that, yes, this is the sampling distribution. It's an approximation because we only used a million different samples to generate this, which is quite a lot. But even after a million of them, a good curve would look like this. And we'll say that this is well approximated by a normal curve. And the thing we just calculated, it deserves a title. This is the approximate sampling distribution, it's a long word, of p-hat. So this collects all the possible values that p-hat could ever be. Looking at that a little bit further, what would you guess the center is? It ought to be that 0.56, the supposed value for the true proportion of successes in this population. It turns out that's actually true by the central limit theorem, that the center of this is p, which is 0.56. Sadly, though, we need a little bit more than that. What we really need, if we're going to ever describe the error right here, it's always good to look at this picture because this is what it's all about. Try to describe that error. To make that happen, we need to know what is the variability. So that's the hard part. We know that the mean mu of p-hat equals p, which is 0.56. So this is a way of saying the mean, using the parameter mu for the mean. But I put of p-hat here, just a subscript, to just say the mean of what specifically. Next thing our author does is he says SD for p-hat. Let's leave a question mark on that, because that's the major struggle right now. The moment we find out what the standard deviation is of p-hat, so how wide this ought to be, we're going to get really close to actually getting a full-on confidence interval and being able to do inferential statistics. But again, we're inching our way towards it. So the major abstract thing is the sampling distribution. As long as all of your samples have the same sample size, This collects into one spot all the plausible values for your statistic. And this is powerful just on its own because if this was really true, if the true proportion of people who say it's not okay to friend their boss on social media, Facebook specifically, at 56%, if this is really true, and we got, say, p hat right here in one study, p hat would be about 0.25 or 0.25 written this way, that would be a major concern. Either that assumption is wrong, 0.56, or maybe the study wasn't a random sample, something went completely awry, because we expect nothing out here. Something occurs, it could be a supremely rare event, or maybe more likely, something else is wrong. Maybe that's a bad estimate of P, or the sample wasn't random like we mentioned. Well, any last questions, folks, with our part B here? Okay, there's a follow-up to this, and it goes this way. Nothing too major. This is the major thing we want to cover. But while we have histograms going, Parsi says, assume that the population proportion of successes is 0.93, wildly different out of nowhere. So if that were the case, just assume, just pretending like maybe that happened in some weird scenario, we want to know approximately how large of a sample is now needed for the sampling distribution of p hat to be approximately normal. Seems like a weird question because when we ran the simulation over here, sample size of 50 did just fine. Larger samples were better, but the change this time is we're changing the true proportion of successes from something that's close to halfway to something that's a little bit more extreme, closer to 100%. Anything that's close to a 0%, say 0.05, or close to 100%, say like a 0.93, 0.97, actually causes massive problems with the sample size. So let's give this a try and see just what happens. Let's move this, I already forgot the number, 0.93. There we go, thank you. If we move this to 0.93, keep the sample size still just at 50, here's what happens to our sampling distribution. Looks like some weird sawtooth, and even more concerned, it has a skew. Would you say that's skewed left or skewed right? Absolutely, we have got a left tail extending out, so left skew on this. No way would we call this normal. Skew's a big problem, and the gaps are just as serious of a problem as well. So we have to increase our sample size. I mean, decreasing it doesn't improve the picture. Let's go to 10 and just show. A sample size of 10, this is what you get. Even more left skewed by a lot, and those telltale gaps. So now let's bump this up to sample size of 100. At sample size of 100, well, it's a better situation. I think everyone would agree. But what we want to use is eventually essential limit theorem. To make that happen, we need a sample size large enough. All it says here at the moment is when n is large and p is not too near 0 or 1, here we're pretty close to 1, sampling distribution of p hat is approximately normal. We need that statement right here to be very accurate. That's where our probabilities are coming from. So this is just not good enough. We need to bump our sample size because that's a substantial amount of skew. So what happens if we bump the sample size? Well, this is why it's called essential limit theorem. The larger and larger your sample, no matter how strange it started out, like this one, sample size 5, you make this larger and larger, and then this converges to a normal distribution. So that's the central limit theorem in action. So let's go up to sample size 100. That's where we had a little bit of skew. And let me know where you'd feel comfortable calling this well approximated by normal. So add 25 to that. That got really weird at 25. We got a weird peak. I don't know if we would be too happy with that one. Let's go up to 150. A little bit more normalized at around sample size 150. And at 200, I'd say that's a big improvement. I'll leave this one up to the class. Would you say at 200, this is pretty good, or would you want to go higher? Let's go a lot higher. How about maybe 250? At 250, well, it got kind of a weird shape. Every time we run this, we have a different 1 million samples, so sometimes they look a little bit odd. But yeah, this is not looking too bad at sample size of 250. Kind of weird that it peaked a little bit right around here, but that's okay. This is all approximate. So let's say at sample size 250, we get this distribution, which can be well approximated by the normal model. So let's put this down here. At n equals, and I forgot the value, I think it was 250, yeah. At n equals 250, the sampling distribution is approximately normal. Normal as in, we have a normal distribution. And notice where the center is for this one. If we set the true proportion is 0.93, and we go to collect random samples all at size 250, every one of those statistics, they go from here to here, they're all close to 0.93. Even on the far end extreme, way out here, that one looks like it's 0.855, something like that maybe. It's still pretty close, 0.875 maybe. And if you're on this extreme, maybe that's about 0.975, not too far off this as well. The center is right at 0.93. But again, the major thing we want to come up with, we still don't have a great answer for, is what is the standard deviation? That's what the central limit theorem is going to answer for us. But any questions at the moment, folks, thinking about these sampling distributions? Okay, we're done with this RStudio stuff for the rest of the entire class. This is just that one opportunity where the topic is abstract enough that it's good to have a picture behind all the madness just to kind of connect the dots. So just one last rehash of this. Sampling distribution takes all of the possible samples at a fixed sample size, collects them into a histogram like this. And if we can find out what the standard deviation is of that histogram, now we can do normal probability computations, which enable us to specify that error right there precisely, once and for all. The result is going to be a confidence interval that we'll be looking at into this same chapter. So going forward, here's where we end up next. The good old central limit theorem does resolve what the standard deviation has to be for the sampling distribution of p hat. Turns into this construct. And this is a result from probability theory, in fact. So one thing that we didn't cover in this book was the binomial distribution. So if you ever read into that thing, that's where that result came from, right there for standard deviation. So here's what the central limit theorem says altogether. The statistic p hat is a proportion of successes in a random sample of size n from a population where we have a true proportion of successes p. If that's the case, then the mean of the sampling distribution is always p. That's what we were doing up here pictorially. The center or the mean is right at the value of the true proportion of successes. The hard statement is this one. Standard deviation is exactly this quantity right here. And the more important statement is when n is large enough, our sampling distribution will become normal, even if the statistic is really close to 0 or 1, excuse me, the parameter rather, is really close to 0 or 1. So we have a couple examples to just try out these kinds of things. These examples are pretty close to what it's going to look like in the homework questions, except that they're not multiple choice. So we're back to the same example as before. I did make a quick edit on this one. I said assume that the sample size was 100, just so that we can calculate something. I also called this part A twice, so I redid my lettering on here to make more sense out of it. So here it says, describe the unknown parameter P using the context. This is actually kind of tricky. And in this problem, we're still thinking of it as unknown, even though there's a value given. Keep in mind the 56%, that's just a guess at the unknown parameter P. it's not exactly what this is going to be equal to whatsoever. So when we go to describe this, we need to keep in mind that the part where it says unknown is just a reminder. P is not equal to 0.56 in this problem. We're just giving a verbal description of what it would be. We actually have to do this kind of problem a lot. So this is kind of like our first look at it. This is not unlike when we were describing a population versus a sample. Here we start off by saying P equals, you could say the population's proportion, you could say the true proportion, anything along those lines is totally fine. Oftentimes our book likes to go this way. P equals the true proportion. Saying true proportion reminds us that we're looking for a specific value. This one is just an approximation. It's not the true proportion, P, for the population. So P will be the true proportion of all, I want to say social network users, because of that statement there. So that's talking about the population. All social network users that, let's pause right here. When we said all social network users, we're referring to the population. That's what makes this one a parameter when we're describing the population itself. And this word right here really keys in that it's a population. We're not talking about the sample of 100 social network users. We are meaning all of them in totality. So let's keep on going. P is the true proportion of all social network users that say it is not okay to friend their boss. When we mention this part right here, we're just saying what the successes are in this study. So when we go to describe the unknown parameter, this is how it always goes. We indicate the symbol. It's either going to be P or mu. We'll look into estimates with mu later on in a different chapter. So in chapter 13, parameter is always P. We have to say proportion somewhere because that's where it is. It's a proportion or a percentage. The population has to be mentioned and the successes have to be mentioned in order to hit the context. Again, it's pretty tricky, but starting in chapter 13, we're going to be practicing this almost routinely on every new problem it's going to feel like. Any questions at all, folks, with our indication of the parameter? Okay, the easiest mistake to make again is to say P equals 0.56 in this response. But just as a reminder, the 0.56 was just an estimate. We still truly have an unknown parameter. Next, here's where this one gets a little bit tricky. This is based off a multiple choice problem in the actual homework section. It said, explain the meaning of P hat equals 0.56 using the context. Well, it's P hat. That keys us in that this is a statistic. This is describing the sample, and that was a sample of 100 participants. So this is a statistic describing the sample with n equals 100. So one way to answer this question, and there's a lot of great correct ways to answer it, but one way to answer it so that my stats lab knows what we're talking about would go about like this. I think the multiple choice is harder in my stats lab because there's like 4 statements you have to look at, and they're off by the tiniest statement. Something could be missing or just a little bit off. Exactly, one word can make something totally true become totally false. And they seem to be really good at doing that. I don't know how they're so effective at it. But so here's the elements that you want to watch out for. If we say P hat is 0.56, that means, because it's a statistic, the proportion of the 100 social network users in the sample. So we started off by just mentioning that we're talking about proportion relative to the sample itself. Because we're using the context, we said not a sample of 100, but the 100 social network users when we mentioned the sample. So the proportion of the 100 social network users in the sample that say it's not okay to friend their boss is 0.56. So that's essentially all we're really going for if you ever have to explain the meaning of p hat. Essentially, it's the same thing we said up here, except we direct our explanation by saying we're talking specifically about the sample somewhere. Any questions, folks, with that portion there? Okay, after getting beyond that part, we'll go back to this statement. Assume that the true proportion really is 0.53. Again, it's just an assumption, so we can calculate something. We now want to know what is the standard deviation of the sampling distribution, and we'll round that to 4 decimal places. This becomes a full-on central limit theorem question. The sampling distribution has that as its standard deviation. So let's write that out right down below, or let's maybe just do a screenshot that does the job. We're doing rule 2 here. So with rule 2, what we need is a value for p. We also need a value for the sample size n. It's mentioned right here with this 100 social network users. And we can now say that the standard deviation of p hat is going to be this quantity. We go square root. And down below right over here, we put in p to start, so 0.53. Then the next portion is q. That's going to be 1 minus 0.53. Then we take that whole quantity, divide by the sample size, which is at 100. So this gives us the standard deviation once and for all. This is a good calculator problem, so let's pull this out. It's actually kind of tricky as a calculator problem. So let me know if you're getting something different, and we'll show different ways to calculate this. By the way, this is something we calculate a lot in chapter 13, so we'll get good at it eventually. It's just frustrating at first. There's 2 schools of thought on this. Some people like to put the whole thing in the calculator just in one shot. Let's try it that way first, and then I'll go the other method of working at it in stages. So if you want to print it out in one shot on your calculator, that's a good idea because you can edit it if you make a mistake or change something there. Start by going second, and what you're looking for is the power 2 button. It's sort of midway to the left, right above where it says log. If you have the up arrow flashing like this, and you press the power 2 button, it'll print out the square root symbol. Now, word of warning, everything stays inside the square root. So if you have 5, 5, but you start printing out 6, 6, 7, whatever the numbers are, if your numbers leave the square root, the bar stops printing up here, we're not doing that computation any longer. So watch out for that in the calculator.
So second and then power 2.
Exactly, yeah. It should look like this after doing that. Then from here, order of operations is actually forgiving with what's inside the square root. Go left to right, top to bottom, and you'll have the right thing. Just don't forget the parentheses. That could mess up order of operations. So go 0.53, parenthesis, 1 minus 0.53, close that parenthesis. We need to divide, so just hit divide, and it'll do that immediately for us. Type out 100. As long as you see the square root symbol going that far, covering the 100, you've got the right thing. So it should look like about this in your calculator if you do it in that order. So to 4 decimal places, we're looking at the 0.0499. 0.0499. 99. And how's it look to folks so far? Are we all getting at that number? Awesome, glad to hear that. This can be pretty frustrating when you're doing this in my stats lab, so that's a reason to take a little bit extra time on this thing. And again, just for the folks who like to compute slightly differently, here's another thought. If you were going to say, compute this by hand, you'd follow order of operations, working inside the innermost parenthesis first. You could start by going 1 minus 0.53, and just hit enter to get a value, 0.47. Immediate next thing is to multiply by 0.53, so just press times 0.53. Where it says A and S, it's referring to your prior answer, 0.47. So we get the 0.2491. And what would you all say the next step should be? Square root or division? Good call. We'll do the division absolutely next. Square root is the last step. So hit divide by 100. Now we have this quantity. What's kind of cool though is if you take a square root of a number below 1, it goes up, not down. It's kind of surprising sometimes. So to square root this, go second, power 2. And then there's a couple tricks. You can hit second and the negative sign to call in the prior answer. On this calculator, I think most people would go up arrow, enter, and just throw the number in that kind of way, the copy paste feature. So now square rooting that gives us the same exact value. So whichever way makes the most sense, I'd say stick with it. I usually go this route, but I'll try to mix it up for folks who like to go in stages. But any questions at all, folks? Getting that number? Awesome. So I said something that was kind of true in a way, but not exactly. It kind of goes that way with statistics. We said we really need that central limit theorem so that we can calculate the standard deviation p hat. And we need to do that so we could describe the error right here. That's the last missing component, the spread. But actually, this is not as fantastic as it might look because we always have to admit the parameter p is unknown. 0.56 was just a best guess. So if the parameter p is unknown, so is the standard deviation because it involves the parameter p itself. We literally put in our best guess right here. So this isn't exactly the true standard deviation unless you know the exact value of the parameter. But in statistics, parameter is the unknown. Our whole objective is to estimate that well and describe the error in estimation. So we need to make one additional adjustment. It's called the standard error. And it's kind of a crazy name when you hear standard error. It's not as if we're making a mistake. It's a way of saying this is just an estimate and we're omitting that. We don't know the true value of p. We can't plug it in a real statistical problem. So what do we do instead? We grab the best estimate that's available to us. Keep looking at that picture. The best estimate is p hat. It's not the true value of p, but it's the best thing that we have once we do the study. So what the standard error does is the following. Let's put down, just for the sake of connecting the dots on this, since p is unknown, the standard deviation of p, which is equal to the square root of p times q over n, is also unknown. It's as if we're back to square one, but we make the following estimate. Estimate the standard deviation of p by saying it's approximately equal to the standard error of p hat, which is this formula right here. So we're just using the estimate for the parameter p, which is approximately equal to p hat. And when you think about it, that's exactly what we did in this problem. The study said that the value was 0.53. That was just their p hat in the study. When we plugged this in, we were really calculating the standard error right here of p hat. But any questions at the moment, folks, with these ideas? Okay, so the standard error is just an estimate of the true standard deviation. That means rule 2 still works for us. What about rule 1? We won't know the mean of the sampling distribution. We don't know the parameter P, but it turns out that is actually okay. We can turn things around and still make a probability computation on P with it being unknown. That's kind of the incredible part about this process. We just really needed the spread. So we're going to estimate it here this way. And what we'll do next on example 3 is just describe how these parts come together. But if you're curious about a preview, here's a huge one. We will eventually say that a 95% confidence interval for P is, take the statistic P hat, add and subtract about 1.96. We'll put in a better number right there in a moment, and then multiply it by the standard error of P hat. This gives us an entire range of numbers. We'll call it confidence interval because it's an interval of numbers, and that's going to be the way we describe the error right here. The width of the interval from the lower bound where we use a negative sign to the upper bound where we use a positive sign is what describes this error right here, making that estimate. So that's where the notes are coming from. And where the number 1.96 came from is just a normal distribution directly out of there. Well, any questions, folks, about standard error? Okay, well, let's take a look at this one. It looks like our last question for the day, example 3. Example 3 starts off by saying, after hearing of the national result that 44% of students engage in binge drinking, which is nicely defined as 5 drinks or more at one sitting for men, 4 for women, a university administrator surveys a random sample of 244 students at his college and found that 96 of them admitted to binge drinking in the past week. So that's a whole statistical problem. This is a real one that we can analyze with a confidence interval, but we're really just doing a pre-analysis on it, looking at all the new moving parts like standard error, for example. But this is actually a pretty tricky problem. It's pretty standard in a certain sense. What's tricky is this said national result for students who engage in binge drinking, and they gave us a value at 44%. That sounds like a value for the parameter, but it really isn't. In fact, even if the population was the entire nation, United States of America, that is still just a guess as well. It's a guessed value of the parameter. But here's the problem with this. There are 2 populations going on at the same exact time. This is really common in statistics. One population is the entire nation. And in the entire nation, 44% admit to binge drinking. Anyone happen to know what the second population is? Well, that would be the sample, but you're on the right track. Exactly, it'd be the other university. Imagine it's like ISU, and the university administrator is like President Reagan or something like that. That's the second population. And we wouldn't say all ISU students represent the entire nation. I mean, it might in small ways, but not in the overall representing everybody in the United States of America. So when we were suddenly talking about a university administrator, that's a totally different population being compared to the nation itself. We need to keep that in mind now when we go to describe the unknown parameter P. Again, we don't know its value. P is not equal to 0.44. So we'll start off by saying P equals the true proportion. We have to say proportions somewhere. In the other chapter, chapter 14, we'll say the true mean because we're dealing with quantitative data. Here, we'll start off by saying the true proportion of all students at this university. Again, imagine that's ISU. That makes it kind of fun, an immediate type of problem. The true proportion of all students at this university, this part's mentioning the population, that, and this part is going to mention the successes. Anyone see what the success would be in this situation? Exactly. It's the admitting to binge drinking that is the success in this problem. Again, that's weird. A success is not necessarily the good thing. It's just something that we're interested in. Why did we decide binge drinking and not binge drinking is what we're interested in? Well, it's kind of the way you said it. When it said 96 of them admitted to binge drinking, they're telling us binge drinking is the success in this problem. That's what they're most interested in. Students who admit that they do that activity. So this right here is a success. I always feel bad saying that to a bad outcome, but it is what it is. It feels even worse if this is like a rare genetic disease or something like that. We'll see that come up. So don't feel too morbid if you called something bad a success. It just means that's what we're interested in the statistical problem. We'll come down here and say that admitted to binge drinking. So that's the true population proportion or the verbal description of the parameter. Again, this is pretty tricky, but we always have to use the context as well. Context came into play when we said all students at the university, and then when we mentioned the successes admitting to binge drinking. Well, any questions at all, folks, with our part A? Okay, this is, again, pretty tricky because it sometimes feels like every different problem, it's like a new scenario and different way to think of what the parameter is. But the more and more we practice this, and we will practice it a lot, the better it comes together in our minds. So if it feels vague at the moment, no worries, we'll get it to that right place. Now, part B is kind of tricky. When it says calculate the sample proportion of successes, what we need to know is anytime this comes up, you're literally calculating p hat. To calculate p hat, we do need a sample size. Let's take a look at this problem again. University surveyed a random sample of 244 students. So let's go n equals 244 students. I usually do that at the start of the problem. I think I just forgot this time. So that's helpful to do as a process because our formula goes p hat, something divided by n. And the numerator is, I'll use hash for number of successes. So we just have a value for p hat. Denominator is the 244 students. Anyone spot the numerator in this problem? Up to it wouldn't be the 244.
No, the 0.44.
It wouldn't be the 0.44 either.
That is the 96.
The 96, good call. So this is the number of successes here. So 96 up in the numerator. I forgot to say what to round on this problem, but I'd say good generic advice about 5 decimal places will give us great accuracy. So back over here, fast computation this time, just take 96, divide by 244. That takes us to 0.3934. Oh, we're going for 5. 0.39344. And notice how interesting that is already. The national result is 44% of the students engage in binge drinking in the United States of America. The university administrator surveyed their university, and it's at about close to 40%. A lot of people might celebrate that. They might say, hey, that's great. Something's working in our university. Look, they're not binge drinkers. That's not true, actually. That's really kind of sad. This value 0.3944 is this value right here, but it's being approximated by a statistic, p hat. And there is error in that approximation. That error could be wide enough that it takes on a lower or upper value of 44% when we actually go to the confidence interval. So when we go to describe the error, we get a range of numbers that goes beyond 44%. What it tells us is this university is not special at all, even though the number looked great at first. We never described the error in estimating the true proportion P. So that's one thing that's kind of unfortunate about getting this value. We can't celebrate early ever in statistics, in other words. Any questions to that stage, however? Okay, so how do we get there to actually give a good estimate? We need to find the mean of the sampling distribution, calculate the standard error. And this is the tough question that I don't know if we're going to rush through it today. We'll finish off when we come back on Wednesday. It's a question just like this one in my stats lab that felt like the multiple choice on it was particularly tough. So I actually wrote a cheat sheet out for that one in case I forget of all the important elements. Well, the last parts here, we're just looking at the central limit theorem. So let's pull this up right here. So part C asks us, what is the mean of the sampling distribution of P hat? If we read the theorem, it tells us the mean of the sampling distribution is P. So we come over here and write P. And notice how unsatisfying that feels. We want to put a number really, really bad, but we don't know that number at all. It's not necessarily 0.44. It's not 0.3934. P is a full-on just unknown quantity. Just trying to go where I might have said that. I don't think I said that on this page here. But because P is unknown, this is all we can say. If the true mean is P, let's say here, P is unknown. Despite it being unknown, we can still estimate it with a confidence interval. The way we do that is we've got to calculate the standard error. That's one thing that we can calculate. And what's the standard error? Well, I grabbed the wrong thing. It's not this. That's the standard deviation right here. And it requires a value of P. We don't have that. Since we don't have the value of P, I should have grabbed this right here, the formula for the standard error. Let's just write it down here. When it says standard error of P hat, notice that problem is kind of tricky as well, just like part B. Some of this is almost like a recognition that the name of the thing gives you this. So the bracket in orange, that's just a way to say standard error P hat. The formula goes this way, square root P hat times Q hat divided by sample size n. And every time you see a Q, it always goes this way. Q hat is 1 minus P hat. So this is our next computation. Just calculate that standard error. Expanding it up, this is what it would look like. So in place of P hat, let's put in 0.39344. Then in place of Q hat, we go 1 minus the same value. 1 minus 0.39344. We divide by the sample size n, which is at a sample size of 244. And that altogether fills out our standard error. Looks like this will be our last computation of the day. Any questions first? Okay, so in the calculator, first thing to hit is second and the power 2 button to call the square root. And then just start typing things out. 0.39344, parenthesis, and 1 minus. 1 minus 0.39344. Don't forget to close the parenthesis. That's the easiest mistake to make there. Hit division. And keep checking that your square root bar continues to extend out. That's another easiest mistake to make. Divide by 244, and this is the value we should be getting. To 5 places, it's a 0.03127. Well, we did it, folks. That's the standard error. And using that standard error, it goes right here, multiplied by our right quantity coming from the normal distribution, added or subtracted to our best guess at the parameter value. That gives us a full-on interval. And the most interesting thing about that interval is, will it capture the 44%? It may or it may not. If it does, it tells us this university is not unique at all. It's just like the nation based off what we know. Well, any last questions, folks, before we call it a day? Okay, well, we didn't quite get to that last question, but we'll finish that off on Wednesday's class. Again, just a reminder, I'll be calling on Tuesday morning to figure out what is going on in our Moodle that's causing people who opted out of the book bundle to not register. It's just like broken links everywhere. So that's gonna be my big task on Tuesday.
Well, I say the usual bundle and it's still in here. Said that I opted out, but when I went around and the did in the open browser, it was fine.
Gotcha,
And then I saved it in the bookmarks, but I
gotcha.
just had to go around it.
Mine's still saved in the bookmarks, but it won't let me in.
It's still.
Yeah, for people that opted out, it's just all messed up
It
now.
won't